So in this video, I want to talk about some properties of the definite integral. Here's one of them. Let's say I take the integral from a to c of f of x and add it to the I got my dx, and add it to the integral from c to b of f of x dx. That equals something. I think you can probably tell me what that something is. Let's go ahead and draw a picture. Now in this picture, I'm going to put a over here, I'm going to put b over here, and I'll put c right in the middle. And I have my curve, whatever it is, y equals f of x. So the integral, the definite integral from a to c of f of x dx is just this area here, or it'd be the signed area if part of it went below the x-axis. This is the definite integral from c to b. That's just this area right over here from c to b. And if I add them together, what do I get? Well, of course, I get the integral from a to b of f of x dx. So that's the first property of integrals. Secondly, the integral from b back to a of f of x dx, we're going to define as negative of the integral from a to b of f of x dx. We could actually do that using the summation, notation, and definition, using the Riemann sums, but I'm just going to make it a definition. So the integral from b to a, putting the second number on the bottom and the first number on the top, is just negative of the normal way. And if you believe this and you believe this, you'd have to also believe this, but we can work it out for ourselves. If we want the integral from a to a of f of x dx, that basically says how much area is under the curve between x equals a and x equals a? Not very much, right? Because a and a are right on top of each other. That has no width at all. So this has got to be 0. And two more properties which we have seen so many times this semester. The integral from a to b of a constant which I'll call k times f of x dx. You can pull the constant right through the integral sign. Just like you can with limits, just like you can with derivatives. We've seen this property so many times. And if we take the integral from a to b of f of x plus g of x, so we have a summation inside. We've already done this with indefinite integrals. This is the integral from a to b of f of x dx. You can just break it up into two definite integrals, plus the integral from a to b of g of x dx. And we see these two rules, they always travel together. At least in our experience, they do. And together they're known as linearity. So I think with these 5 rules, we ought to be able to get pretty far. Now, I just want to do a problem or two. Let's say you know that the integral from 1 to 4 of f of x dx is equal to 8, and you know the integral from 1 to 2 of f of x dx is equal to 3. And I ask you to find the integral from 2 to 4 of f of x dx. Well, we're just using property number 1. Let's sketch ourselves a little picture. So we know this, and we're trying to find that. Whatever this curve looks like, 1, 2, 3, 4. We know that this whole area under here, from 1 to 4, is 8. We know that the area between 1 and 2, that little area is 3. I'm asking you to find the area between 2 and 4. You could use this, you could just sort of visualize it, but you know that the integral from 1 to 2 of f of x dx plus the integral from 2 to 4 of f of x dx is equal to the integral from 1 to 4 of f of x dx. In other words, the area of this little region plus the area of this region equals the area of the whole thing. Well, I told you that this is equal to 3. We don't know this. Well, you probably know it by now. And we're told that the area of this equals 8. 3 plus this equals 8. Subtract 3 from both sides. The integral from 2 to 4 of f of x dx equals 5. If the area of this little region equals 3 and the area of the whole thing is 8, this has got to be 5.